Great, so let's tackle a basic example problem. So this is our basic example problem. The whole aim is that we solidify a little bit these concepts that we've tackled up to this point. So we've essentially done everything now up to the point except for looking at the surface tractions. So we can go from a displacement field to strains, from strains to stresses, and we can even check if those stresses are in equilibrium. So this is what we've done so far. I'm going to do a simple example problem, the simplest one I can, to illustrate this point clearly. I'm going to do it by hand, and then afterwards we're going to tackle this problem on Python. Okay, so then we're going to do this sort of a Python example of this problem. So here's the problem at hand that I want us to tackle. So essentially, I'm going to start off by saying I've got some three-dimensional prismatic bar. Okay, on this side I'm going to have a uniformly distributed traction, call it T. So this thing's unit is essentially in meters squared. So that is essentially like a pressure that's distributed on this thing. But that's what we have, stress. I think of that same unit. And in essence, so it's not the same as a stress. It's just it's got the same units as stress. So, okay, so that's just important to take note. Here is essentially my prismatic bar. I'm going to do is choose my coordinate system such that I am in this direction in positive y, in this direction along the axis I'm in positive x, and then in this direction I'm in z. Okay, so that is just to have a coordinate system that we have, so right at the back of this little plate there. And then this plate here at the back is sort of completely fused with the back. Okay, so it's completely clamped at the back there. So just to make sure that you understand that we've essentially taken this prismatic bar and made sure that it cannot do any Poisson's contraction or anything like that. It's really just completely welded shut at the back there. Okay, well, that's essentially the problem that we have. The other thing that we need to just talk about is what is the geometry. So this is L, this distance here. This height is going to be 2c, and this out of plane, or this in z direction, this width is going to be 2d. Okay, so I'm going to write down a field for the displacements that somebody's now proposed. So this is the problem that we want to solve. So this is the problem, or this is the problem that we want the solution for. And we're lucky somebody comes along and says, here's the solution. So here somebody says, here's my solution. Here is my solution to the problem, and gives us a field. It says, okay, so the solution I got to the problem is the following. This is the field for W. What I just maybe want to do is, forgive me, but I just want to maybe write it explicitly as a function of x, y, z. I just want to remind you the whole time, this is a function of x, y, and z. Although there's only an x here, there could have been other terms. It was a more complex problem. Okay, so what we have to ask ourselves now is, does this even make sense? So let's just first see what's your expectation. So if I were to pull on this bar, I would expect things to elongate, and I would expect this point to move the most, this point to not move at all. So this is now the displacement part, okay? So as I pull on this bar, this tip here is going to displace the most. This tip can't displace because it's fixed, but in consequence is because this is fixed and this point is displaced, there's essentially a stretch individually internally in that bar. Okay, so there's going to be lack of stress developing in there. So does this even make sense from that point of view? So if I evaluate x at 0, what do I get? I get essentially a displacement in the x direction, because that is what U stands for, the displacement in the x direction, that is then 0. Okay? If I evaluate at x equals to L, what is my displacement of a point on this face here at the front? Well, let's plug in x equals to L. And then I can still evaluate for any point for y and z to be on that face. Luckily, it's not a function of y and z, so it means it's sort of constant. Doesn't matter what y and z I choose, I'm going to get the same displacement. That whole face stays parallel to that back face, so everything displaces the same amount. But if I plug in a L in here, I get T over EL. That's essentially what I get out. Okay, so that is that displacement that I've got. Okay. So that is the first part. So this checks out just sort of a sanity check. Other sanity check is, does this thing even make sense from a units consistency point of view? We're claiming this is the displacement field. Does this even have the units of meter? So let's check. So I've got a traction, a T at the top, that is Newton per meter squared, divided by E at the bottom, which is the material, which is typically something in gigapascal. But essentially it's Pascal over Pascal. So that cancels out and multiplied by distance, and that is meters. So the units check out. Okay. And I can make the same arguments for these ones at the units check out because Poisson's ratio is dimensionless. So that is just make sure all of that makes complete sense. So the units check out, that's great. Let's check what happens if I pull this bar, and let's just imagine now what's going on here. So essentially, if I'm here in the front and I'm pulling on this bar, what would happen? Okay, well, the fact is the bar will get longer, and my expectation is that the bar will get sort of thinner. Is that behavior captured? Let's check. So if I evaluate the bar, plug it in, let's say at x equals to L. So I've done that. Now I can evaluate at y and different places. I can evaluate y at 0. At y at 0, it stands still. Nothing moves. Okay? That's in the center of the bar. And that sort of makes, that completely makes sense because that bar will now essentially contract like that. Poof, it will go smaller like that, but that center point would not move. But if I were at the top, let's say at C, then it's minus Poisson T over E times C. And the same for the bottom. It would be minus Poisson T over E times C. So that contraction would be then the most from the top and bottom is the signs. Does that make sense? So let's check. So if I go up in positive Y, I expect a negative displacement, yeah, because it needs to contract. So if I go positive Y, I get a negative displacement. That makes sense. If I go negative in Y, I expect to see a positive displacement. A negative in Y, so minus C, that will become a positive. Boom, it will go positive. So that makes sense. So this makes sense. Okay. And the units, as we've spoken, also make sense. Let's just check at the backplate if the boundary condition there is satisfied. So U must be 0 everywhere. If I evaluate it for any x or y or z, this U field must evaluate it to a 0 because that is a fully clamped sort of fused boundary condition at the back there. Let's check what happens if I do that. If I plug in an x equals to 0, which is where how I'm going to get myself into that backplate. So to get to the backplate, or the back of this, sort of the back surface, let me call it a backplate. Ooh, backplate. To get to that backplate, I need to essentially evaluate my U field at x equals to 0 because that's how I'm on that surface there. So x equals 0, but to stay on that surface, I can still walk around in y and in z. So y and z I'm leaving as values. And if I do that, plug that in, I get a field that is 0. What this is telling me is that this U field satisfies 0 everywhere. So that satisfies what we expected to see. Okay, so that is fantastic. So this satisfies the boundary conditions beautifully. Let's look at V. If I go for the V field, also I want to be at the backplate. I need to substitute for x equals to 0. That's how I'm on that back surface. So essentially U, and then I have y and z. So I can still walk around there. But this field must now also be equal to 0. Okay, but let's see what happens if I plug in now x equal to 0. When I plug in x equal to 0, I get minus T over E y, okay? And if I now walk around here at the back, up and down in y, what I see is I don't get a 0 displacement. Okay, so this boundary condition, so the back surface, let's call it boundary conditions, BC, boundary conditions. This one is not satisfied. It's only satisfied at one point, and that is if I were to evaluate this expression at y equals to 0. Only there does this thing represent what the problem is supposed to, what I wanted to try and represent over that whole phase. It's only captured at one point where it's accurate. For the rest, if I were this height or this height, the thing would still contract at the back there, which is not what we wanted to model. Okay, so this is essentially a problem. If I go for the W field, and again, I want to be at the back plate, I evaluate x equals to 0. I get then, if I plug in x equal to 0 into this expression, I get and again, the same story, does not satisfy. If I move around in Z away from 0, it's not satisfied. It's things still contracting, it's supposed to be fixed. Okay. So that is an important point to make. So although somebody has given us sort of analytical expression, something that's nice in a sort of a polynomial format, and although this is claimed to be an analytical solution to this problem, the point I'm just trying to make here is it's still an approximation to the problem. It's not exact. Okay, so just because formulas are given in terms of x, y's, and z's does not mean it's exact. Okay, it can still be approximation. So what we see is here, essentially, this does not satisfy it, so it's only an approximation. Approximation, not exact for this problem. So this claimed solution that somebody gave us, or this solution I gave you, wrote down, so here's my solution to the problem, is only an approximation. And so this is an important point to make, because as you'll see later in the course, the fact that this is an approximation opens up the door to say, well, if a lot of problems that are even simple as this one, we can't really get closed form solutions that are accurate, that are exact, they are only approximate in any case, then we're completely fine just approximating all solutions. And the reality is, the sad part is if you were to pull on this structure, and if you were to imagine where stresses could involve that could be high, if I were to clamp that thing at the back plate, there might be some high stresses developing there that I'm not capturing at all. I'm only capturing the actual component of the stress with this solution. And so that's why it's also then good to rather go and say, let's approximate solutions in general numerically. That's what the finite element method is going to be about. But if we approximate those solutions numerically, the benefit is that that we might even get more accurate stress solutions out around those edges out. So that the places that are critical, that we don't make overly simplified approximation, but rather have something that is a bit more accurate there. Okay, so I'm going to pause this video and start in the next one. I'm going to keep it in small tidbits so that it's easy to download. There are some students, unfortunately, that are struggling if the videos become too long. So I'm going to keep the video sort of shortish so that I can break it down into multiple steps. Okay, thank you. So this is part one of this basic example problem.